All right, well, we shall begin. Happy Friday, everybody. Oops. All right, so we are continuing our lectures on numeric methods. We left off talking about root finding methods, and there was one method, bisection method, that I briefly introduced, but I've got some pictures to go along with it in this lecture. We'll also look at some derivative approximation, and we'll introduce this topic of optimization. So let's go ahead and take a look at bisection method. So bisection method, one of the few kind of root finding methods that is guaranteed to find a root. As long as you have a continuous function, if you have a continuous function and it's negative on one side and positive on the other side of an interval, we can guarantee that we can find a root within that interval. So we have that. So we just kind of bracket off the root. We say, well, if we know a root exists in here, we just kind of keep shrinking that interval, the size of that interval in half until we're confident or until we feel good about having the value. So, again, we just require that the left-hand side and the right-hand side, when you evaluate the function, they have opposite signs, and we can kind of ensure that by making sure the product of the function on the left-hand side and the function on the right-hand side is less than 0. So it doesn't matter if the left is positive or negative, it's just that the left and the right-hand side have to have opposite signs. Okay, and the way our algorithm works is we will calculate the midpoint. If the midpoint happens to be a root, we'll go ahead and stop there. Otherwise, we evaluate the function at the midpoint and ask what is the sign of that, and we're going to keep the pair of points, whether it's the left-hand side or the right-hand side, and the midpoint, so that they have opposite signs. And we keep doing that. The size of the interval keeps shrinking by in half, and eventually we get to where we're headed. Okay, so here is an example. This is a function we're going to look at: log of x minus e to the negative x, and from our previous examples, we know that the root is around 1.3098. But here I'm just going to kind of bracket it off and just start off at 1 and 2, and we'll see how it finds the interval, finds the root. And so, without any pictures, we can just let this while loop run, and it finds the root at 1.3098 after 24 iterations. And even though it looks like there's several lines of code, it's actually very, very, very simple. So we have the right hand side of our interval, x on the right and x on the left, and as long as that difference is greater than our tolerance, which I've arbitrarily chosen to be 10 to the minus 8, we'll keep going. We calculate the midpoint. We'll evaluate the function at the midpoint, and if the midpoint is equal to 0, we use all equal to get approximately equal to 0. If it's approximately equal to 0, then we'll quit and break out. Otherwise, we will just evaluate the function at the left multiplied by the function at the midpoint, and if that's less than 0, then we know the root has to be between the left and the midpoint, so the midpoint becomes the new right-hand side of the interval. Okay, and if that's not less than 0, then we know the midpoint, the root has to be between the midpoint and the right-hand side, so the midpoint becomes the new left-hand side. And then we just repeat over and over again. So we just update to what our new left or right-hand side of our interval is, and we evaluate the midpoint over and over. And we just keep going, and then when it finally quits out, what's the midpoint between the left and the right, and that's going to be our answer. So it takes us around 24 iterations to get within 10 to the minus 8. So it is one of the slower algorithms because it converges, just keeps cutting our interval size in half, but it works, and it is guaranteed to kind of find it. So here are some pictures. My interval starts off on the left-hand side at 1 and on the right-hand side at 2. The left-hand side, the function evaluates as negative, and on the right-hand side, it's positive. Now, here I've drawn the function in a blue line just so you can kind of see what's happening. But in reality, we don't actually know the value of the function everywhere. Otherwise, we would just say, oh, the function crosses 0 right here. But here we're just going to say, all right, I've evaluated the function on the left, it's negative. I've evaluated the function on the right, it's up here, that's positive. And then I calculate the midpoint and I evaluate the function at the midpoint. So that's also positive. So I'm going to get rid of the right-hand side. I'm going to bring in the right-hand side to be the midpoint because we know the root has to be between the left and now the midpoint because these have opposite signs, negative and positive. Okay, and then so at the next spot, I'm going to calculate the midpoint, which is going to be around 1.25, something around here. That's going to be negative. So I'm going to keep basically the point, right here and right here. So at the next interval, we take the midpoint of that, and we end up between here and here. And then at the next iteration, I will cut this in half. So right around here in the middle. And when I evaluate that, that's going to be positive. So we'll keep, basically between, we want to make sure the root is, between the negative and the positive sides. Then I'm going to cut this in half. And when I cut this in half, I think it ends up like right around here, which is just ever so slightly positive. Okay, so we throw that away, and so the root is going to be between this point and this point, very close to this point, but so that's going to be that. And then so at the next interval, I cut this in half. We're going to throw away that side, and that at the next iteration, I cut this interval in half again, and we throw away that side, and we just kind of keep going and going and going, and you can see after around, this is just how many iterations is this? So 1, 2, 3, 4, 5, 6. After 6 iterations, 2 to the 6 is 1/64th. The width of my interval is 1/64th of what I started. Okay, so fairly small, and we can keep going, keep cutting it in half. But at a certain point, you can probably switch over algorithms to switch from bisection method, where you're cutting it in half, over to Newton-Raphson, because Newton-Raphson converges much faster as long as the function is well-behaved. Well-behaved means as long as it kind of looks like a straight line in this small interval, and I would say if we zoom in here, it does look a little bit like a straight line in there. So Newton-Raphson will probably work quite well, and we can switch over to that. Okay, so Newton-Raphson is very high performing in that it does find roots very quickly, it converges very quickly. But the problem with Newton-Raphson is it's not guaranteed to converge. And if you try it on some place where the function isn't well behaved, isn't approximated by a straight line in that region, it is it might not perform well. So this use kind of bisection method to kind of bracket off the root into a small enough interval, and whatever that is, then switch over to Newton-Raphson, and then kind of do the last couple iterations, 1 or 2 more iterations of Newton-Raphson. Okay. These are a couple slides talking about the orders of convergence. Okay, and basically you're looking at how much does the error, the approximate error between your root and the actual root is. So the actual root and your approximation of the root, how much does that error shrink at with every additional iteration? Okay, and so with the bisection method, we're cutting our interval size in half with every iteration, and so our order of convergence, we have linear. The order of convergence is 1. because at every interval we're cutting the size of the interval in half. Okay, with Newton-Raphson, I'm not going to. I just leave it at. It can be shown that basically at Newton-Raphson we have much faster convergence. We have a quadratic convergence, second order convergence. Secant method is something in between, around 1.6. But yeah, Newton-Raphson converges faster again, but we just don't. We have the problem that it's not guaranteed to converge. But we like bisection method, and here's a couple little pictures of showing it cutting in half there. Okay, let's talk about another method here. This is a method to approximate our derivatives. Okay, so the Newton-Raphson algorithm can be used to find roots, and we said to find the next value at your next iteration, take your current value and then subtract off basically the rise divided by the slope. That's going to give us the size of the run on that kind of triangle. So the rise is going to be the value of the function at x at time n, and then the slope is f prime. Okay, the derivative at xn. Okay, so this requires us to find the derivative, and so when we implement this on our computer, we can use calculus to find the derivative. And so if you have a simple function like log of x minus e to the negative x, okay, finding the derivative is straightforward enough. Okay, derivative of log of x is 1 over x. Derivative of e to the negative x is negative e to the negative x. And so if I've got a negative here, then it becomes plus e to the negative x. And I can code that up. I've got f is log of x, and f prime is 1 over x plus e to the negative x. And I can evaluate the function at, say, 5. Okay, 5 is 1.6027, and then the derivative is going to be 0.206, 7379. I plug that in, I can get my next iteration, so on and so forth. And so again, the f prime gives us the slope of the tangent line. And so here is just a plot of, if I plug in 5 into my function, it's right here. And then if I draw a tangent line, it looks like this. And that f prime is going to give me the slope of the tangent line right there. Okay. Now, in some cases, we might be in a situation where calculating the derivative, is hard for us, okay? And in that case, we can approximate the derivative numerically, right? And again, the guideline here is if you can find your answer analytically, that's almost always going to be better than using a numeric approximation. Okay, these numeric methods should only be used if the analytic approach is tough. But if you want to avoid derivation running calculating derivatives, we can do this. Okay, so the idea behind it is that, well, we say, what's the definition of a derivative? Okay, and so this was probably covered, during your first week of calculus. As he said, you start off with limits, and then you say, okay, well, the derivative is going to be, evaluate the function at a, okay, and then add on a small little h, okay. You're going to evaluate the function at a plus h. How much does the function change between the value of the function at a and a plus h? Okay, basically, how much does the y change? And you're going to divide by how much x changed, which is going to be h. And we're going to take this as h goes to 0. And basically, rather than taking the limit as h goes to 0, with our computer, we're just going to plug in a small value of h, maybe like 10 to the minus 5, 10 to the minus 6, and we'll get an approximation here. So that's what we'll do. So here, my approximate derivative, my f prime approximation, I'm going to just plug in h is going to be 10 to the minus 6. I'm going to evaluate the function at x. So I'll plug in x, log of x minus e to the negative x. I'm going to also evaluate the function at x plus h. So I'm going to do log of x plus h minus e to the negative x plus h. Right? So I get the value f of x and f of x plus h. I take the difference between those two values, f of x plus h minus f of x, and I'm going to divide by h. And so if I plug in 5 here, and I say print out 12 digits, this is going to be the result of using this numeric approximation. And the result there is 0.2067379236669. Okay? And then the actual value, or at least using the actual derivative function here, where I use 1 over x e to the negative x, so that's the result of doing the calculus. If I use that function and I plug in 5, I get 0.20673794699. Okay, so we're accurate to around 7 places after the decimal. Okay, 2067379. Okay, and it's after the 9 on the approximation. I have 23669. On the actual value, it's 2067379, and then only this part. These last few digits, 46999. Is a little bit off. Over here, it's 23669. Okay, but other than that, I'd say accurate up to seven decimal places is pretty good. Because again, we're going for approximations, and I'd say yes, indeed, we do have a pretty good approximate answer here. Okay, now what I did here is I took h, which is 10 to the minus 6, and I added that. Right, so I took 5 and I basically did 5.0001. Right, and I said, how much did the function change? Now, someone else could say, well, what if instead of going to 5 and 5.001, what if you did 5 and 4.999? Okay, what if you had added a negative h instead? Would that change our answer? Okay, so when you do a limit, you can do the limit as h goes to 0 from the right, or you can do the limit as h goes to the 0 from the left. And on a continuous function, those two things are going to be the same, but something like tangent of x or whatever, as pi over 2, they go to opposite directions. But anyway, here I've got a negative h, and I do the exact same function, right? Log of x, or function of x and function of x plus h, but this time my h is negative. I say, what is the value of the function there? Okay, so here, when I use the actual f prime, the true value, again, I have 2067379, and then my last few digits are 46999. Okay, when I take the negative approximation, okay, I'm accurate to 7 decimal places again, 2067379, and then my last few digits are 70299. And then if I take the right-hand side approximation, accurate to 7 decimal places, 2067379, but then it's the last few digits are 23669. So basically, the digit after the 9 is 4 on the true value. On the left-hand side approximation, it's a 7, and on the right-hand side approximation, it's a 2. Okay, so one side it's too high, and one side it's too low. Now, too high by only a little bit and too low by only a little bit, but that's what we have. And when you have curvature in your function, generally one side will end up being too high and the other side will end up being too low. Okay, now so if it's like concave down, the left-hand side will be too high and the right-hand side will be too low. If it's concave up, then the left-hand side will be too low and the right-hand side will be too high. Okay, this is an illustration that is grossly exaggerated. Right. So again, here we are trying to find the derivative when x is equal to 5, and the derivative is shown. The function is the curved blue line. The derivative is shown by the slope of the dotted red line. Okay, so the dotted red line is the actual slope. And here I have kind of an exaggerated approximation. where I plugged in 5, and I basically do the left-hand side approximation. So I'm going to draw kind of a line, a point at 5, and I kind of draw a secant line through 4. And you can see, because of the curvature, the slope of the orange line is too steep, okay? Because it's connected down here and up there, so the slope ends up being too steep. Meanwhile, if I use the right-hand side approximation where I have a positive h, I'm connecting at 5 and 6, and so my slope in green ends up too shallow. Okay, it's not steep enough. Okay, now this is, highly exaggerated. Okay, where I'm using an h of +1 and h of -1. In our diagram, our slopes are off only by a tiny bit because I'm using an h of like 10 to the -6. But this is just kind of a magnification of the issue. One side is too steep, one side is too shallow. So what we can do is basically, I can say, hey, why don't I just take the average? Take the average of the left-hand side, which is too steep, and the right-hand side, which is too shallow. Why don't I do that? And so basically, I'm going to calculate my balanced approximation by doing x plus h and x minus h. So here I have h is 10 to the -6, and I'm going to calculate f of x plus h, so that I've got log of x plus h minus e to the negative x plus h, and then f of x minus h, so log of x minus h minus e to the negative x minus h. I take the difference between those two values, the plus side and the minus side, and then now the difference between my x's is going to be 2h. So I'll divide by 2h. And if I do that, now I'm accurate to around 10 places after the decimal. So I have 206737949, okay? And then my last two digits are 84. Whereas over here I have 206737949, and my last two digits are 99. So we've improved our accuracy, by like 3 orders of magnitude. Okay, we've got we went from like 7 decimal places, or 7 places after the decimal of accuracy, to now around 10 places of accuracy after the decimal. Okay, so quite a bit of improvement by balancing the left and the right hand side. So this is how we can approximate a derivative. Okay, now here I've just been using the same function over and over. With R, functions themselves are objects, and so you can pass them in as arguments of other functions. So you can have a function where it takes in an argument of another function. And you've seen that with like the apply family of functions in R and things like that. You can pass functions in and it will take that function and use it. So here I can generalize my function, and we're going to call this function just f derivative, okay? And it's going to be a function where we take in as an argument a function, and then some value of x, and then some quantity h, which we will default to be 10 to the -6. And then we're going to calculate the left-hand side, x minus h, the right-hand side, x plus h. Then I'm going to find the function on the right-hand side, the function on the left-hand side, take the difference between those two things, and divide by 2 times h. And this is going to give me an approximation of the derivative of the function at x, whatever the function is. Okay. And so with this, now we have a way to approximate a derivative without having to do any kind of calculus. All right, let me give you your first view quiz answer, which is the letter D. D as in dog. I believe, yeah. Okay. All right, so here is, if my function is log of x minus e to the negative x, I plug this in, I get, again, 206737946 9, and the last two digits 84 are off. here's just a very, very simple function. We're going to say my function is x squared. All right, so the derivative of x squared is 2x. So we can just see, okay, how accurate are we? Okay, so I can say, all right, what is the derivative of this function x squared at 5? And if I plug that in, it says it's 10, and that aligns with what we expect because we're expecting 2x. Okay, now I could say, all right, give me 12 digits, and we can see we are accurate to 10 significant digits. 1, 0, 10, and then 1, 2, 3, 4, 5, 6, 7, 8. 8 places after. So a total of 10 significant digits of accuracy. 10.0000000014. So we're off by a little bit, but pretty accurate in my opinion. Okay. So that's what we have there. Okay. Now, when you look at the definition of the derivative, right, it says take the limit as h goes to 0. So when we're dealing with real numbers, yeah, we can take the limit as h goes to 0, and you say, well, okay, what if instead of adding 10 to the minus 6, I added 10 to the minus 7 or 10 to the minus 8? You might say, well, why don't I just shrink h to be as small as I can possibly go, right? And for real numbers, yes, that is what we are doing. But we are not dealing with real numbers. We are dealing with floating point numbers. And so when you have floating point numbers, you can't just keep shrinking that h to be as small as you can, because you run into like computational inaccuracies, right? So the smallest possible value we can add is our machine epsilon, which is going to be 2 to the negative 52. We can add that to 1, and if we're not dealing with 1, if we're dealing with 2, then the smallest value you can add would be 2 to the negative 51, and then if I'm on like 256, then it's going to be like 2 to the negative 44. As my numbers get bigger, the smallest value I can add also scales up. Okay, and so just to kind of illustrate some of the the issues that we run into, I say, print a whole bunch of digits, 16 significant digits, and I'm trying out different sizes of h. So if I do h is 10 to the minus 5, I think I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 places, 9.99999, accurate to 10 significant digits, and kind of our last 6 are off. If I have 10 to the minus 6, also accurate to around 10 significant digits, 1.000000000, and then the last 6, 139.778 are off. If I shrink it down to 10 to the minus 7, now I'm only accurate to around 8 significant figures, 10.0000000. Oh, okay, maybe 9. Okay, so and I'm off 2804313. So the last 7 digits are off. Over here, the last 6 digits are off. At 10 to the minus 8, or the last 1, 2, 3, 4, 5, 6, 7. So around 9 significant figures are accurate, but the last 7 are off. Here I'm adding 10 to the minus 10, and now the last 8 are off. Okay, and at 10 to the minus 12, look, we're at 10.000. We're only accurate to around 5 significant digits, and then over here 889. These last whatever digits are, our accuracy is dropping. So shrinking the h to be smaller and smaller and smaller on the computer doesn't actually improve our accuracy, because we're not dealing with real numbers. We're dealing with floating point numbers. Okay, if I try 10 to the minus 14, you can see now it says 9.769. Now we're not even, it's not even 10, right? It's sure it rounds off to 10, but we're getting more and more off. 10 to the minus 15, now we're off by quite a bit. 8.88 is our derivative approximation versus the true value of 10. And then at 10 to the minus 16, it just zeroes out, because at this point we've reached the limit of what the computer can tell between values. So if I do 10 plus 10 to the minus 16 and 10 minus 10 to the minus 16, I think we've surpassed machine epsilon, and the computer can't really tell the difference between what is 10 plus 10 to the minus 16 and what is 10 minus 10 to the minus 16. Here, let me just verify that. Oops. So if I say A is 10 and B is going to be 10 plus 1e minus 16, is A equal to B? Yeah. So the computer can't tell the difference between 10 and 10 plus 10 to the minus 16. Okay, whereas if I added 10 to the minus 15, it is able to tell the difference between them, but it's it's the difference is very small, right? So let me see. All dot equal A and B, right? So the computer would say these are approximately equal when you do A and B. They're not exactly equal, so the computer is able to distinguish A and B, but the computer would evaluate that and say they are approximately equal here. All right, so that is something you have to keep in mind. So here my default value for my derivative approximation is 10 to the minus 6, but this is kind of assuming your value of x is somewhere around, between 1 and 10, basically. Okay. Obviously, if your value of x is like 1,000 or 1,000,000, then your h has to be considerably bigger. Okay. Otherwise, you're going to run into these same issues of trying to add too small of a h that the computer is going to have a hard time distinguishing. Okay. We're running into catastrophic cancellation. Catastrophic cancellation is when you're subtracting off two numbers that are very similar to each other. So even if the numbers themselves are not that inaccurate compared to the actual value, when you subtract two values that are very similar to each other with floating point arithmetic, any kind of inaccuracies or just those things are highly magnified. So keep that in mind whenever you're dealing with floating point numbers. Okay, but anyway, we have a method for approximating a derivative. So as long as we don't try to add too small of an h, we do have a method of approximating our derivative, and it works well. And with that, we can now kind of turn all of our root finding methods into optimization methods. Okay, so in our last lecture, and also, I guess at the beginning of today's lecture, we covered root finding methods. We said you can do Newton-Raphson method, secant method, fixed point iteration. These are all ways to find where the function is equal to 0. And all we have to do now is we say, all right, well, let's find where the derivative is equal to 0. Okay, if we can find where the derivative is equal to 0, that's going to find local minimums and local maximums, or basically critical points of a function. Maybe a saddle point, but when the derivative is equal to 0, that's going to correspond to local minimums and local maximums. And so now we have a way to find to perform numeric optimization. Okay, so if you're like a data theory major or math major, you can take a course on optimization. Even if you're not, you can take a mathematical course on optimization, and there's lots of stuff, a lot of theory behind it. Here we're just spending just one or two short lectures on this topic, just very kind of cursory glance of seeing how we can perform some numeric optimization, just because it is something we do quite a bit in statistics, but we're not going to get into a lot of theory stuff. A lot of our optimization methods are written for finding local minimums, and if you want to find a local maximum, you just take whatever function that you want to maximize and you multiply it by -1, and you say find the minimum of that function, and that will figure out where your local maximum is. Okay. This first class, though, when we do derivative-based numeric optimization, this is going to just find critical points. Okay, so we say, all right, let's take the derivative of the function. let's find the roots of the derivative, and that's going to correspond to critical points. We evaluate those critical points. Some of those are going to be local mins, some will be local maximums, and some might be saddle points, okay? And but that will work as far as a way for performing numeric optimization, okay? So again, if you can find the derivative analytically, that's going to be the best way to go, right? But if you can't, we have a way to approximate them. So if we want to do Newton-Raphson method for optimization, basically we just take the Newton-Raphson algorithm and we're going to say, let's find the roots, but not of f of x, but find the roots for f prime of x, okay? So Newton-Raphson for f prime of x is going to end up looking like this, all right? We're going to say, all right, if you're currently at x at time n, then your next iteration, x at time n plus 1, is subtract off, take your current values, x at time n, subtract off the value of the value of the derivative, f prime, divided by f double prime, okay? Because basically the function that we want to find roots of is f prime, so we do, what is that function divided by the derivative of that function? So f prime divided by f double prime, and we keep going, and eventually this thing is going to, f prime is going to be approximately equal to 0. It's going to be less than whatever epsilon value is, and that's when we say, all right, we found something that's close enough to a local min or local max or critical point or something, okay? For this to work, f double prime has to be twice differentiable. So I think that's, that's straightforward. Obviously works best for smooth and continuous functions. And then f double prime, it just can't be 0 where you evaluate x at time n, okay? It's allowed to be 0. It's allowed to cross the x-axis. That's not a problem. But if where you're evaluating at your, during your iterations, if x at time n, if the second derivative equals 0, then you run into problems. So if you need to, you might have to choose a different starting location, and with a different starting location, you might be able to find it. So f double prime is what? It's 0 at like inflection points, right? When it switches from concave up to concave down and things like that. So that's where things would start to break. Okay, so here's just a very, very simple example. I've got this polynomial 0.25 x to the fourth minus 0.5 x squared. I use calculus and I say, all right, the first derivative is x cubed minus x, and my second derivative is going to be 3x squared minus 1. And we'll use that and we'll do Newton-Raphson method. All right, here is, this is how we're going to find the next iteration. So here's a plot of the function 0.25 x to the fourth minus 0.5 x squared. This is what it looks like. We've got a local max at 0, a local min at 1, and a local min at -1. Let's see if we could identify these, okay? So here's my function f. As far as my algorithm goes, I need to code up two functions, f prime and f double prime. So f prime is x to the third minus x, f double prime is 3x squared minus 1. And this is just the Newton-Raphson algorithm. I'm going to just say, all right, start off at some arbitrary point, 2.1. Your next iteration is going to be, your old location minus f prime at the old divided by f double prime at the old. And then we'll just kind of run that forever in a loop. Okay, so I have while the difference between that is greater than our tolerance, we'll just keep going. And it converges and it finds 1. Okay, so it says, oh yeah, I found the local minimum at 1. Okay. If I start off at a different location here, I start off at 0.9. And it finds 1 as well. Again, approximately 1.000 something 308. Okay, great. Here I start off at 0.1 and it finds approximately 0, 10 to the minus 24. If I start off at -10, it gives me -1. So that seems to work. Let me just show you. So here. I also just kind of want to show you how the derivative approximation thing, really, it does work, okay? So here my function f is 0.25 x to the fourth minus 0.5 x squared. Okay, and again, here's my function for approximating derivatives. I have the left-hand side is going to be x minus h, the right-hand side is going to be x plus h, and we're going to take the function on the right minus function on the left divided by 2h. Okay, so that's my derivative approximation. So here's my function. My function is f. So what did I do? Unexpected this. Oh, I've got an extra curly bracelet. Okay, so my function is f, and I'm going to just write two more functions. My f prime approximation is, I'm going to just say, hey, give me the derivative of f at x. Okay, and now I have a way to approximate my derivative here. Okay, so remember the actual derivative f prime itself is going to be x cubed minus x. So f prime itself is x to the third minus x, and so my f prime approximation, all I did was just say plug in f here. And so if I say, hey, what is my approximation at 10? It gives me this 989.99999, whereas f prime itself at 10 gives me 990, right? So we can see the approximation. Again, it's an approximation, but it's decent, right? And I didn't have to do, one of the nice things about numeric methods is you don't actually have to do much thinking. You just say, well, taking derivatives is hard, all right? And then what about the second derivative, okay? What is the second derivative? You just say, all right, give me the derivative, f derivative of which function? The f prime function, okay? My f prime approximation function. I say, do that, okay? And that's going to work. Now, your errors, okay, the actual f double prime is this. And we can say, all right, well, how does this compare? So I can say, all right, what is f double prime at 10? F double prime at 10 is 299. My f double prime approximation, it's a little off, 299.11. Okay, so basically the amount of error kind of continues to grow and grow. But again, we're just, we're looking for approximations. Okay, but anyway, I've got my approximate f prime, I got my approximate f double prime. So I could just say, hey, you know what, let's start off at some location, and can you find, local min's at 1, and it got 0.99999, all right? What if I start off somewhere else at like 0.2, all right? And yeah, indeed, it finds something close to 10 to the negative 23. So something close to 0. So it's working. And again, you could put in any other kind of function that you want. Here I can do like, let's find the local mins and maxes of, say, like sine of x, okay? And I'm going to just say, hey, f derivative of f double prime of f, we're going to try that again. Let's plug in 0.2, and this gives me 4.7. 4.7, what is 4.7? Is that close to pi? Pi over 1.5 pi? What is that? 1.5 times pi? Yeah, so it's pretty close to 1.5 pi, right? If I put in 0, oh, it didn't like that. Okay, because 0 is already at, 0 is at the inflection point, right, for sine of x, so that's not going to work. But if I do, I don't know, let's do 1, okay? So that gives me pi over 2, pi over 2, so that, something approximately equal, things like that, okay? So that's that. So we have kind of this whole class of optimization methods that are based on derivatives, and again, if you can analytically find the derivative, that's the best way to go. But if you can't, we have a fairly reliable way of approximating our derivatives. Okay, that's it for today. Let me give you your second and third view quiz answers, which are the letters E and A. E as an elephant and A as an apple will be your second and third view quiz answers for today. All right, we'll wrap things up there. Have a great rest of your day. Have a great weekend, and we'll see you next week.